Hello everyone, hope everyone is doing well. My name is Ann Njeri. I'm a third year PhD student at the Georgia Bank Center for Astrophysics. And in this talk, I'll be discussing the wide field VLBI technique and how we've used this technique to study very radio faint sources in the Gusnell field using the very long baseline array, the VLBA, and the European VLBI network, the EVN, survey that Albin welcome. I'm going to give you a scientific background, why VLBI, discuss the wide field VLBI technique, and also give you some of our results from this survey, and also give you conclusions based on our survey. One of the main goals in astrophysics is study the history of star formation and galaxy evolution across cosmic type. And as shown on this Lilly-Maddow plot, the star formation rate tends to peak at a ratio of about 2. Further study of AGN activity in these distant galaxies have also shown that AGN activity tends to peak at ratios between 1 and 2, closely following the evolution of star formation. As shown here on this Shankar plot, showing the AGN activity as a function of time or ratio, AGN activity is shown to peak between ratios 1 and 2. And this coevolution between star formation and AGN activity in these distant galaxies implies possible feedback mechanisms. Further study of these faint or distant galaxies in the radio band shows unexpected upsurge of the number source counts at sub-Milijansky levels. Shown here on this Pedovani plots, showing the number source count density as a function of flux density. Further resolving this region here below the 1 Milijansky, the flux density below 1 Milijansky, we see that the population is mainly composed of star-forming galaxies and active galactic nuclei, and the active galactic nuclei is further subdivided into either radio-quiet AGN or radio-loud AGN. These regions are highly obscured in the X-rays, infrared, and optical, and we know that the radio band does not suffer from dust extinction, therefore it offers unbiased tracer for both star formation and AGN activity. Further bringing the concept of interferometric radio continuum surveys, which offer high angular resolutions and high sensitivities, which are in turn able to detect cyclotron emission from AGNs, thereby has the capability to distinguish between AGN and star formation. When we bring in the concept of very long baseline interferometry, whereby this technique is only sensitive to very high brightness temperatures of above 100,000 kelvins, and at this redshift level is only a clear indicator of the presence of AGN. Observations with the Velier meter at arc-second angular scale resolution and are insufficient to spatially resolve AGN from star formation activity in these distant galaxies. Just further to note that the Emerlin observed that sub-arc-second angular scale resolution as well, and is only partially able to resolve some of these radio galaxies. Shown here on this plot, they're showing a comparison of angular resolutions of various deep interferometric radio continuum surveys that are currently ongoing, such as the MIGHTY with Meerkat, Cosmos, eMERGE. And just key to highlight that we see the EVN and VLBA have milli-arc-second angular resolutions and are in turn able to image these distant galaxies at parsec scales. And just to highlight that the blue and the red lines just show the early to late type galaxies as seen in the optical band. Therefore, the VLBA provides a powerful extinction-free tool to search for these faint AGNs and to spatially resolve AGN from star formation. Other probes of VLBA other than the AGN, we have gravitational lenses and dark matter, tidal disruption events, and of course this very famous first image of a black hole. So historically, the VLBI technique has been limited by a small field of view, whereby we've only been able to image the central few arc seconds. And this was further compounded by time and bandwidth mirroring. However, recent development in correlators, increased bandwidth and supercomputers have enabled correlation of the VLBI data at extremely high spectral and temporal resolution, which has in turn allowed the imaging of the entire primary beam. And the advantages of imaging the entire field of view is that it increases the sample size and you're able to see multiple science targets in a single observation. For example, we have these results from observation of the Kuznets field with the EVN. So this field has previously been surveyed with the VLBI, the EVN, and this study by Radcliffe tripled the number of sources detected from 12, from the 12 sources that were previously detected with the VLBI survey to 31 faint VLBI detections. Some of the techniques that have made the wide field VLBI technique possible include the multiple phase center correlation and the multiple source self-calibration. So the VLBI sky is sparse, and so correlating the entire primary beam makes no sense at all. And this results in huge terabytes of data. And most of the time, 99%, this is just noise. So what do you do? Instead of just correlating blindly the entire primary beam, we instead correlate simultaneously on multiple positions across the primary beam. What do we mean with this? So, for example, this image shows a theoretical wide field EVN survey of the M82 system. The yellow circle shows the EVN primary beam. The blue markers shows the phase centers, and the blue circles shows the area to which the both time and bandwidth mirroring of the array has been constrained to less than 10%. So these, you can basically see that we have placed the phase centers on the plane of the M82 system instead of the entire primary beam. So the phase centers are pre-selected to either cover the entire primary beam or on sources of interest or on non-radio sources, e.g. using the VLEA positions. So this technique will result into lots of small data sets in gigabytes. And yeah, but the good thing is that you can use the same calibration across all the data sets, thereby making this multiple phase center correlation easily realizable. Therefore, a large number of phase centers can be correlated with high time and frequency resolution in a single correlation pass, and we're able to target hundreds of objects in a single run. So the other technique that has enabled the application of the wide field VLBI technique is the multi-source self-calibration. We know that ionospheric and atmospheric effects tend to reduce the image quality in phase reference observations. And also considering that we're observing very faint regimes at Makrojansky levels, therefore the sources are not suitable for self-calibration. So what do? We combine a response of multiple sources across field of view to perform self-calibration. So for example, here we have two images of the same source. The first image, just the standard best referencing of self-calibration has been done on this source. And then on the second source, we apply the multi-source self-calibration technique, whereby the source has been divided by a clean model made by combining multiple observed targets or sources in this field to derive a clean model. And this clean model is able to reveal point source structure with a high signal to noise. So some of our results are just a description of our survey. The goods field node has been observed with both the EVN and the VLBA, and it's the only extragalactic field that has observations with both the EVN and VLBA, just offering two data sets of VLBA observations. So the goods north field, the pointing centers are basically based on the candles field, where the VLBA covers the entire candles field. And the right panel here just shows the multi-wavelength coverage of the goods north field. Just draw attention to the black circle here, which shows the observation of the VLA, EMALIN, and the EVN. And then further to draw a circle to the region highlighted in blue, which is the Hubble Space Telescope coverage. And this is the same region as the candles region. Thereby, we have this region covered by the VLBA and the outer region also covered by both the VLBA and the EVN, sorry. So we detected 31 sources at a sigma of 6 using the EVN, and detected 24 sources at a sigma of 5.5. And just the unique thing to highlight is that the extraction method that we use in this case, whereby we know that there's a source at that position, and therefore we are able to extract the source at this low signal to noise ratios. So some example from our results. So this is one of the strongest sources in our observations. So as seen here, using the VLA, this is clearly an AGN, since it has these jet structures. Then you bring in VLB observations at millisecond resolution, so able to resolve of the jet and reveal a compact core, which looking at this VLA image, you're not able to deduce whether there's anything at the center of this image. Similarly, we have this faint source. Just looking at the VLA image, you will not be able to infer whether it's an AGN or there's any AGN activity, since we lack structures such as jets. But bringing observation with the VLBA, you're able to reveal a compact core, both the EVN and the VLBA. This is one of our most interesting source in our survey. So as shown here, we had this source observed with the JVLA, EMALIN overlaying the optical counterpart, and the VLBA position highlighted here with the red cross. So this source has a signal to noise ratio of 5.7. As mentioned earlier, we know that there's actually a source at that specific point. Therefore, we are confident at this signal to noise levels. Clearly from the images, you can see that the VLBA position does not coincide with the peaks in both the JVLA and particularly the EMALIN. You can see the peak of the flux density in the EMALIN image and the position of the VLBI position. So clearly, this is a merging galaxy system where both the star formation and AGN activities are co-evolving. Yeah, just a conclusion that when looking at the JVLA and EMALIN only observations, you're not able to infer whether there's any AGN activity, but then you bring in observations with the VLBI and you're able to detect AGN. So just implying this is a co-evolution of both star formation and AGN activity. So conclusions, I've seen in the previous few slides, both intermediate and VLBA resolutions are important in deep field surveys. And particularly this survey, we've combined imaging using the JVLA, EMALIN, and the VLBI. And this gives an SKA2-like data set. For example, shown on this figure, we have observation with the VLBA, the EVN, the EMALIN, and the VLA, and just covering a parameter space that can only be achieved using SKA2. Therefore, this data set can be used for key technical verifications for relevant SKA pathfinders. Again, many SKA fields will not be able to identify all extragalactic AGNs. This is due to maybe insufficient resolution, lack of fine infrared telescopes, WISE is too shallow, and the ALMA field of view is quite small. Therefore, VLBA will play a very important role in identifying AGN in these distant fields, especially if no radio access measurements are available. So yeah, that's all from me. Thank you for listening, and our team is ready for your questions. Thank you.